Alright, here we have period of oscillation. Period of oscillation is in quantum mechanics is just like you can think of classically, but here we have to rewrite some units. T is in fact now equal to pi over omega. Omega is the frequency, which makes sense because this will be in frequencies per second, so this will be in seconds. Also, this omega frequency is equal to energy over this h bar, and this relationship comes from here. So you can rewrite these to be like this, and then bring h bar down. Therefore, the frequency of oscillation is equal to this, just restating that. H bar is equal to h over 2 pi, that's useful conversion. Second point on this page. The total energy of a 2D or 3D system, a wave function, will be the sum of the 1D energies. So for this, if we were given, for example, a three-dimensional particle in a box, that's an example. For a three-dimensional particle in a box, you have the energy of a 1D. Let's say in the x. Then you have the same energy in the y. Well, not the same energy value, but the same energy function. And then in the z, and the sum is equal to the energy total for the 3D. That makes sense? Next is qualitatively, if you have some sort of graph of potential, let's say this is a particle in the box, so here we have 0, 0, here we have infinity, infinity, and some sort of potential, v of x. If v of x varies, then the negative of the second derivative of the wave function must be greater when the potential energy is low. So, by analogy, in classical, alright, so let's back up a little bit. In classical mechanics, total energy is equal to kinetic plus potential. And that's it, right? So, if you increased K, then, potential would have to decrease in order to keep the same energy. If K decreased, you would have to increase potential. So, here where there's maximum potential at these ends, from 0 to length r of this box, there's going to be 0 kinetic here and here. And where there's a minimum of potential, there's going to be a maximum kinetic. So let's draw that now. Like that. Right, so this is what we just drew. If the potential is high, then the negative of Ke is small. Here's already a pre-drawn graph. How nice, look at that. I don't think I drew these correctly, but the idea is the same. If you have strong concavity for the kinetic, then you have a high kinetic energy there, and conversely a low potential. So what do I mean by strong concavity? By strong concavity, quantitatively, you can see that this curves more into the x-axis than, for example, this curve. See, this curve takes a long time to curve back, while this one goes whoop, right back down. So to exaggerate it, you know, that's a strong concavity, because you know your differential x's are going up at a very high rate and then go right back down at a very high rate, versus this, oh, it's taking a long time. This is going to be low kinetic energy, high kinetic energy. And for some v of x potential, then, you know, correspondingly it's higher where kinetic energy is going to be lower, then lower when it's higher. And that's just restating that. Interestingly, you can have this type of graph, where you have the kinetic energy seemingly reaching some sort of asymptote here. You can almost imagine some sort of horizontal asymptote where it's trying to get to, and then it just doesn't. It folds back on itself. It has downward concavity when v of x is positive and when k is negative. This is classically forbidden. Classically, this region is forbidden. What does that mean? It means that there is a point of inflection which indicates a node. These are the two nodes here. Now, usually a point of inflection, let's go back to this graph. Usually a point of inflection occurred where the kinetic was crossing the x-axis. Here, node occurs when it's below the x-axis, and this is classically forbidden, because what does that give us? This gives us a negative kinetic energy. Isn't that crazy? That's so crazy, right? Well, interestingly enough, the more nodes there are, the higher the kinetic energy. And the more nodes, the more energy you're going to have. Therefore, when we're talking about the lowest energy state of some function, the lowest energy state has no nodes. It does not have any nodes. This was just restating what we said earlier. Curvature. Curvature is concave down when psi is greater than 0. So concave down when psi is greater than 0, and concave up when psi is less than 0. That makes sense. And the final term for this review of the first quiz, degeneracy. There's a number of different energy states within an eigenvalue. This should be within an eigenvalue. So trying to connect this to other chapters. You know, if you have electrons in this orbital and electrons here, this energy state, so this is some energy state I, energy state J, this energy state would be doubly degenerate. right? Because it's at the same energy level, but there are two ways that you can have that energy state. So that's what that means.